My name is Emanuel MP. I'm a PhD candidate in the Power System Research Laboratory of Chulalongkorn University. I will be presenting our research titled The Performance Assessment of Supervised Machine Learning-Based Approaches for Photovoltaic Diagnosis. So this is part of our ongoing research, co-authored by my advisor, Associate Professor Surachai Chetosoni, and Professor Watit Benjapolako. So this is the outline of the research, and this brings us to the introduction of the research. So consistent with the United Nations Sustainable Development Goals for 2030 on sustainable and affordable energy and sustainable and smart cities. So this research aims to provide solutions and innovative solutions that would enhance the sustainability, reliability of solar PV cells. So solar PV cells, as we already know, so they convert sunlight into electricity using the photovoltaic effect. However, this is subject to numerous anomalies due to their method of installation, which exposes them to elements of nature and other environmental factors. So like weather conditions, component deteriorations, improper installations and maintenance concerns. This eventually creates conditions that impede its operations and reliability over time. So it has become very important to profile strategies that would ensure the dependable and efficient electricity production through solar cells, because the conventional method that was used in the past is no longer adequate. So machine learning, as we know, is a branch of artificial intelligence which uses data to train machine to think and mimic human thought processes. So in this research, the supervised machine learning algorithms were used to train and supervised machine learning models to detect anomalies and inefficiencies in the solar PV dataset that was collected over the period of 1 year from the Tapsake solar PV farm in the Tapsake district in Prachap Khirikan province of Thailand. So this brings us to the problem statement, the research objective, and the research contribution. So the contribution of this research will be to enhance the performance and reliability of photovoltaic systems through the early detection and diagnosis of various operational faults. So the figure below shows the Tapsake solar PV plant schematic diagram, which tells us how photovoltaic effect is being performed by converting the radiant energy from the sun through the use of solar modules, which an inverter is used to convert this DC into AC power, and a step-up transformer is used to step up this power to required voltage, where the metering and then connected to the Thailand electricity grid. So this shows the physical architecture of the Tapsake solar PV farm and its PV panel technology and layout. So the Tapsake solar PV farm is divided into 5 zones as seen in the diagram. We have the zone A, zone B, zone C, zone D, and E, and it has 4 different types of PV technologies as seen on the table. So this shows the methodological flow charts where data sets collected by EGAT, the Electricity Generating Authority of Thailand, over the period of 1 year from January 1st, 2019 to December 31st, 2019. This data set is preprocessed. Linear interpolation was used to treat the missing values. The data set was formatted and cleansed, and data analysis was applied. Feature extraction was also applied. And the preprocessing, then the training, validation, and evaluation of this data set by employing several evaluation metrics, as we'll see in subsequent slides. So this shows us the correlation matrix of this data set. This reveals the underlying relationship and interdependencies of the features that were collected in this research It's plant capacity, active power, generating capacity, ambient temperature, global radiation, and module temperature. So it's obvious from the charts that global radiation shows a strong positive correlation between global radiation and active power and plant capacity. So this implies that the amount of sunlight that directly reaches the solar PV farm is directly proportional to the amount of power that is generated, which makes sense. So this brings us to the distribution of the data sets all through the year from January to December. So it is seen from this distribution that the highest feature is around the month of March, which corresponds to the hot season in Thailand, and the lowest is around December, which corresponds to the winter season in Thailand. So the data labeling was performed using kernel density method for percentile feature estimation, where each anomaly were assigned values from normal to short circuit faults to abnormal voltage, partial shading, and hotspot fault, corresponding to 0, 1, 2, 3, and 4 respectively. So the predictive model that was applied was a classification-based prediction technique, where the ML model was trained, validated, and tested on 8,760 solar PV data that were partitioned into 3 subsets with a partition ratio of 70:15:15 for training, validation, and for testing. So the evaluation metrics employed were the accuracy, the precision, the recall, F1 score, and the confusion matrix. So these were used to evaluate and understand the performances of these machine learning models. So this shows the result for the first supervised machine learning model, which is a decision tree. So it shows a training accuracy of 100%, a validation accuracy of 100%, test accuracy of 100%, recall, precision, and F1 score are also shown. So the confusion matrix below shows how effectively this decision tree performed in correctly classifying and diagnosing the faults within the solar PV data sets. So the decision tree confusion matrix for this test set will be the basis by which we judged the performance of each of these machine learning models. It can be seen that decision tree performed very well in correctly classifying the anomalies that existed within these data sets. The same can be said for LSTM, which is the long short-term memory, having a test accuracy of 96.04%. So it can be seen that although the LSTM performed quite well, it had a hard time correctly classifying these anomalies within the data set of the solar PV. So this brings us also to the multilayer perceptron algorithm. So the test accuracy shows a 95.13 test set accuracy. It's also had a hard time correctly classifying and diagnosing the anomalies within these data sets. So the CNN 1D, which is the 1D convolutional neural network, also performed quite well, having a test accuracy of 91.2%. And the confusion matrix shows how it's correctly and incorrectly classified the anomalies within these data sets. So convolutional neural network 2D CNN also performed quite well, achieving a test accuracy of 88.97%, and the confusion matrix shows how it struggled in correctly classifying the anomalies in the data sets. So the TCN also shows quite a good result, having a test accuracy of 88.96%, while the confusion matrix shows that it's misclassified a lot of the anomalies in the data sets. So the k-nearest neighbor shows a good test accuracy of 96.73%, and the confusion matrix shows how it's correctly and incorrectly classified and diagnosed the anomalies within the solar data sets. So the random forests algorithm performed exceptionally very well, achieving a test accuracy of 99.85%, and the confusion matrix shows how it's correctly classified the anomalies within the data set. So this brings us to naive Bayes accuracy, having a test accuracy of 88.13%, and the confusion matrix shows how it struggled in correctly diagnosing and classifying the anomalies within the solar PV data sets. So we have the support vector machine also achieved a test accuracy of 88.97%, and the confusion matrix shows it's correctly and incorrectly classified the anomalies within the data sets. So, and lastly, the linear discriminant analysis, which is the LDA, achieved a test set accuracy of 86.0%, and it struggled in correctly identifying and classifying the anomalies within the data sets. So this shows the performance visualization and ranking of the machine learning models that were modeled to diagnose and classify the anomalies that existed in these PV datasets. It can be seen that the tree-based models, they achieved better results, or better overall results and performances compared to other models. So the random forest achieved the first, which is the first and the best performance, followed by the decision tree and KNN and others. So this brings us to the results discussion. So the result from this study, it validates and substantiates the claim that machine learning algorithms are capable of diagnosing faults in PV systems. So these ML models were evaluated using accuracy, F1 score, precision, and recall as metrics, with the results demonstrating that the tree-based, as we said earlier, machine learning algorithms like random forest and decision tree, they performed best in correctly diagnosing and classifying defects in PV system with a 99.85 accuracy on the test data. So the research aims to enhance PV capacity monitoring and automation by making them more dependable and efficient, which in turn would effectively lead to an increased adoption of PV technology and subsequently a reduction in carbon dioxide emission in the environment. So we conclude by saying that this paper offers a performance assessment of several machine learning based techniques for photovoltaic cell diagnosis, having gathered and pre-processed data set from the Tapsake solar PV farm, which is a small scale 5 megawatt solar PV installation in Thailand. So the research aims to improve fault diagnosis and automation in PV installations, thereby making them more reliable and efficient. So the implication of this study is the study has the potential to enhance the performance and reliability of PV systems through the early detection and diagnosis of various operational faults. This would in turn help facilitate proactive maintenance and optimizations of PV systems. So the future research would aim to integrate these ML models into real-time monitoring and control systems for PV to determine their efficiency under dynamic conditions, including their resilience to data latency and anomalies. So the researchers would like to acknowledge the Rachel Pesek Sunford Fund for the Center of Excellence in Artificial Intelligence, Machine Learning and Smart Grid Technology, and the Second Century Fund of Chulalongkorn University. So acknowledgement is also expressed to the Electricity Generating Authority of Thailand for providing the data sets that was used in this study. So this is the research team comprising Professor Watit Benjapulaku, Associate Professor Surechai Chetesoni, and my humble self, Emanuel MP. Thank you.